Hi guys, this video is on second isomorphism theorem of advanced group theory. It states the two factor rings Hn by n and H by H intersection n are isomorphic to each other, where H is a subgroup of G and n is also a subgroup of G, but n is normal in G. And also we have Hn defined by the product Hn, where H belongs to H, n belongs to n, is a group. It is a subgroup of G and the subgroup n is normal in the subgroup Hn. And we have H intersection n, which is a subgroup of G, is normal in H. And these two facts are due to the fact that n is normal in G. Now we proceed to the proof. First we consider the canonical homomorphism gamma from G to G by n. Second, we restrict this gamma to the subgroup H. This time gamma from H to G by n is also a homomorphism, but with kernel H intersection n. Let us see this situation in diagram. The subgroup H, the normal subgroup n, and a portion of group G by n. Then gamma, it maps H1 of G, that is also element of H, to the coset H1n. Likewise H2 to H2n, and the elements of the subgroup n to the subgroup n itself. So the elements of H intersection n, these are also the element of subgroup n. These elements of H, this portion of H, they are mapped to n. So we must have the kernel of this homomorphism is H intersection n, because the elements of H that has image n are also the elements of n. So from first fundamental theorem, we can define an isomorphism from the factor ring H by H intersection n to gamma H, and mu1 be that isomorphism. And if you remember from first fundamental theorem, gamma from S to gamma S is a homomorphism with kernel H intersection n. Then you can define mu1 from H by H intersection n to gamma H as an isomorphism. And this gives us the factor group H by H intersection n is isomorphic to the group gamma H. Now let us define mu1. And if you remember from our previous theorem, if phi is a homomorphism with kernel S, then we have phi inverse phi A equals to AH. This means the element of domain that maps to phi A are the elements of the set AH. And so we have gamma maps the element of H1 H intersection n to the coset H1n, because the kernel is H intersection n. So we have the function mu1 from the group H by H intersection n to the group gamma H. Mu1 maps the coset H1 H intersection n to the coset H1n. Likewise the coset H2 H intersection n to the coset H2n, and the coset H intersection n to the coset n. This is the definition of function mu1. Now the second part of the proof, here we restrict gamma to the subgroup Hn. So gamma from Hn to G by n is also a homomorphism with kernel n, because the elements of Hn that maps with the set n are the elements of n itself. Also we have the set Hn equals to the product Hn, H belongs to H and n belongs to n. So for H1n of this set, its image under gamma is H1n capital N, and that equals to H1n clearly. And H1 capital N is an element of the set gamma H. So the range of Hn under gamma is gamma H itself. And now from first fundamental theorem, we can define an isomorphism from the group Hn by n to gamma H, and let that isomorphism be mu2. And this shows the group Hn by n is isomorphic to group gamma H. Now we define the function mu2. And again we recall the theorem phi inverse phi A equals to AH, where H is the kernel of phi. This means phi, it maps the element of the set AH to the element phi A of the range. And with the same argument, gamma, it maps the element of the set H1n capital N to the element gamma H1n of codomain. And we know this set equals to H1n, and this set is also equals to H1n. So the function mu2 is the function from the group Hn by n to the group gamma H, such that it maps H1n of domain to H1n of range itself, and S2n to S2n, and the set n to the n itself. And we can see the isomorphism here. Now we reach to the conclusion. First, we showed that the factor group H by H intersection N is isomorphic to the group gamma H. Second, we showed that the factor group Hn by N is also isomorphic to the group gamma H. And from first and second, we can conclude that the factor group Hn by N is isomorphic to the factor group H by H intersection N. At last, let us present this situation in a diagram. The function mu2 is a function from Hn by N to gamma H, and mu1 is a function from H by H intersection N to gamma H. Mu2 it maps H1n to H1n, and mu1 it maps H1 H intersection N to H1n. So mu1 inverse it maps H1n to H1 H intersection N. We can see the isomorphism here between the groups Hn by N and H by H intersection N. Isomorphism. Both of these groups are isomorphic to gamma H, therefore they are isomorphic to each other. Now if you define a function phi from the group Hn by N to group H by H intersection N such that phi equals to mu1 inverse mu2, then we have phi of H1n equals to mu1 inverse mu2 H1n, that equals to mu1 inverse H1 capital N, and that equals to H1 H intersection N. And phi is an isomorphism from Hn to H by H intersection N because the functions mu1 inverse and mu2 are also isomorphisms. So this shows the factor group Hn by N is isomorphic to the factor group H by H intersection N, and this proves our theorem.